Hello, welcome to video 16 in the lecture Advanced Mathematic Modeling. In this video I want to introduce you to the method of generating functions, which is a very powerful tool to calculate moments or characteristics of a probability distribution, and it's maybe a bit advanced technique, but sometimes that's the only one where you can really find analytic solutions. So let me introduce what we mean by a generating function. We define this first for a general sequence of numbers, and later I will then apply this to a discrete probability distribution. So assume we have a sequence of numbers. So we have here a set, and then we have the numbers a with index I, and this is discrete, so I runs from 0, 1, 2, and so forth. So this is just a sequence. Now we define the generating function. Give this name capital S, and we introduce a new variable. This S is a continuous variable, and then we say that is this infinite sum. So we take the ith element of our series and multiply it by the argument of the function to the power I, and here our index I runs from 0 to infinity. So here we assume this sequence, the sequence of numbers is infinite. If the sequence is finite and it stops at a certain value, then we just can replace all the rest elements by 0. And since if we take this function and if all a values beyond the finite size are 0, then this generating function is not changed. So what we got from a discrete sequence to a continuous function. We write it like this: we achieved a continuous function. So you say this S here is a real number. Sometimes we say also it's we can assume it to be a complex number, but for our purposes it's enough if we say this S is a real number. Now you can also say, okay, look, does this object exist? So we have here an infinite sum of values. Does this converge? And then one can show, I mean, this will converge if this S is small enough. Yeah? And so typically, so we say this S, maybe the absolute value, if we allow negative numbers, should be smaller than 1. But typically also we will only consider positive values of S. So basically then you have S between 0 and 1. And then this function, really converges. Now, so what's so special about this way, how this generating function? So it has some nice properties. So assume we have two sequences. AI and BI, so not only a single one, but two of them. And now we can look what is the sum. The sum is again a sequence which is defined as just the sum of the elements of the sequence. Yeah, so that's how when you have two sequences can generate a new sequence by summing the elements. And since this here is a linear operation, you can directly see the sum has generating function. We take the generating function of the first sequence, and then we just sum the generating functions. We take the generating function of the second sequence. This is then the generating function of the sum of the sequences. So that's already nice. And with these properties, these generating functions start to make more sense or get interesting, because then you have simple rules how to generate new generating functions if you know some of them. So if we have here a rule for the sum, is there also a rule for the product of two generating functions? But here it's not so simple. You cannot just multiply the product of elements. We need some bit more complex operation. So, and for this we need the convolution of two sequences. So what do we mean by convolution of two sequences? So we want again to generate a new sequence C, and this we define now the sequence. The nth element of the sequence is given as A0 Bn plus A1 Bn minus 1 plus A2 Bn minus 2 until An B0. Sometimes people also call this the, here, looking at the star here for the convolution. So it's a kind of product, but not a normal product. It's this kind of thing. So, but to be clear what this really means, this is really a sequence. So you have to calculate these C's for all kinds of values. So let's look. What is, first that's the definition. So what is C0? This is just A0, B0. And then what is C1? This is A1, B0 plus A0, B1. And then you get the second, first zeros, the second element of the sequence. This is, here's, yeah. So, but that's, in order to follow this, we should have reverted this somewhere. So let's do it like as we say here. So the second is A0, B2.
Das hier.
So A0, B2
Ich bin da.
plus A1, B1 plus A2, B0. And so on in this way. So you see, you generate a sequence where later elements in the sequence are computed by taking longer sums of values. And now the question is, so what is the generating function of this? We want to know what's the generating function of C. So the generating function of C is the Cn times S power n, where the sum over all n's from 0 to infinity. And so we sum from 0 to infinity. But for the Cn's, now we have to put in this here, and we can write this as a sum, where the index I goes from 0 to n. So these are these values. We have AI times Bn minus A to power S of n. So here for the C we have introduced here this sequence. Now when you work with these sequences, now we want to change this expression in a way that we obtain the generating function of A and B. And so the first thing what we do, let's write this A here. The sums come later, so with this AI. Now I take some part of the S's here, the first I powers of this, then here I take the B, let's say minus I, and then I take here the remainder of the powers n minus a. So you see, if you multiply these two s functions, we have again this here. And now I change the sums, and I do this in such a way, because you see this here doesn't depend on n. So here I sum over the I, and here I sum over n, because here these terms depend on n and I. And now, what is the order of the range of values the sums have to go over? You see here in the sum we get all values from all pairs of n and I, where I always must be larger than n. And so we can replace this by a series where I goes from 0 to infinity, but n must be larger than I, so n equals 1 to infinity. And then you see this is just the product of two generating functions. So you have here the generating function of A times the generating function of B. So if this is not so clear that you can do it like rewrite this like this, so I recommend you that you write down the first values of this sequence when n is small, and just write down all the terms and see that you can rearrange the terms in such a way that you can factor this here out. Sometimes in this way it's a bit too abstract. So, but what we have seen here, if you take the product of two generating functions of two sequences, yeah, this gives the generating function of the convolution. So this is here just two properties of the generating functions, but so far we don't really know what this is good for. It's just a way to transform a sequence to a real valued function. Now let's see how can we apply it to a discrete random variable. So we apply this generating function to a discrete random variable. So this works only for discrete random variables. When we have continuous random variables, one can do something similar, but I want to keep it with the discrete random variables, whereas it's also the case where I know the most applications of this technique. So we have a random variable x, which goes from 0, 1 to 3 and so on, and we have the corresponding probabilities. So we have p0, p1, p2 and so on. So that's the probability that our random variable has a certain discrete outcome. And now we can define for this random variable, or for the whole distribution of this, we can generate the generating function as the expectation value of a new variable s to our x. So how is such a so it's the generating function is an expectation value, and we know how to what does the expectation value mean. That's actually the expectation value is something which every function of our random variable is associated to a value, and so we do this by taking our function s of x, we take it for all outcomes e, and weight this outcome by the probability of the random number e, or I, yeah, s to I times the probability of I. So what you see, so the generating function of the whole discrete distribution is just the generating function of the sequence of these probabilities. And this we can express as the expectation value of S to X. And maybe to as a side mark, when we calculated our moments, I mean, so far we used the moments to characterize a distribution, and what we could do for the moments, we calculated the expectation value of our random variable to some powers n. And here n went to all kinds of numbers. And now the generating function. What we do, we calculate the expectation value of s to x. So it's again the subtle difference if we either take a power function or an exponential, because s to x we can write as e to ln s times x. So that's an exponential. We take the expectation value of an exponential of our random variable, and for the moments we take the expectation value of power of our random variable. And this, again, the small difference what's here has this tremendous differences. Yeah, but first, so it's in principle something similar as we did for the moments, and this also means that if we know this expectation value for all s, so if we know this for all s, we have our function of s, then basically we have the full information of the discrete probability distribution encoded in here. So once we have this simple function, we can recalculate all probabilities of our distribution. So this f of s is then called sometimes it's called the probability generating function. The probability generating function of x, or some people also call it the characteristic function of the random variable. And keep in mind, this object is just a function which we can plot. So it's a function of our value s, which goes between 0 and 1, and we have here our function s. Nothing else than this function is what we want to have. So for every fs value, we want to calculate this expectation value. And now what are the properties of this function? So first, maybe, does it exist? And that's as before. Existence. Since all our pi, and even the sum of the pi, is normalized to 1. Yeah. So this means these p values are small enough, and if the s are small enough, this will always converge. So this means this converges for s smaller than 1. But basically I just want to plot it between 0 and 1. So we have a convergence if for small value. So now how can we calculate this function? And then we will see basically we need two things. We need to know how does this function look in the neighborhood around 0, and how does this function look here at the right side around 1. Yeah? So let's see what we can say about the function at 0. Now, so we have here to put in 0 here, so we have either 0 to some power, and now maybe I write this here, we need to know something. So if we have, so either we have terms s to power 0, or we have s to powers k, where k is not equal to 0, because we put in 0 here for s, and then we have 0 to something, and it can either be 0 to 0 or 0 to k. So we want to know what's the limes when s goes to 0 of these two things, and in this case 0 to 0 is 1, and in this case 0 to something else equals 0. So this we have to keep in mind when we calculate the values of s for s equals 0. And if we do this and plug this in here, so we see only the first component remains. Yeah? Because for all other terms in the expansion of the sequence here, we have 0 terms, and only when I equals 0, then this is 1, and then the P0 stays here. So we know already this function here starts with the first value of our first probability. And so let's see how can we continue. So maybe let's first look what the value is here at the value of s at s equal 1. F at 1, when we put in for all the s1, and then we just see the sum of all our probabilities, they're normalized to 1, so we see this here goes to 1. So we see our generating function is a function which starts from P0 and then ends up at position 1 with 1. So the next thing we could ask, what is the slope of this function here? And for this, maybe we should look first what's the derivative of this f of s. Maybe I start a new paper for this. So what is the derivative? df over dS. And so you just take the derivative in our sequence. So we have our pi and then I times s to power I minus 1. And then you see in this derivative the first term doesn't play a role anymore, so here we just sum only from 1 to infinity. And similar, we can take the second derivative, and we have again a sum. We have our pi, and then we have I times I minus 1 to s to I minus 2, and here we only need to start from 2. And so on and so forth. You can take higher derivatives. And now with a very similar argument, how before we said that f at position 0 is P0. Now if we look if we take the first derivative as to 0, and then we see only P1 remains. So this means that if we take the derivative of our function at s equals 0, we obtain the second value. So the slope of our generating function at 0 is the second value of our probability distribution. Now, when you take the second derivative here, and at position s equals 0, basically you find this P2, but we still have here normalization by I times I minus 1. And so when you think this through, you will find that we can in general write the coefficients, the nth probability in our discrete distribution. We can write 1 over n faculty as the nth derivative of our generating function at the position s equals 0. Sometimes we write this also like 1 over n faculty times f, so the nth derivative we write like this, f nth derivative at the position 0. And so this is the first important formula for the generating functions. So once we were able to obtain the generating function, we just take derivatives at 0, and the derivatives encode the whole sequence of probabilities. So the absolute value, the slope, the curvature, and so on, this encodes the full probability distribution. So now what's happening here at the positions, at the behavior of this function at 1? Let's look at this. So what's the behavior at s equal 1? We have already seen f at 1 is normalized. So what's the derivative doing at the position s equal 1? When s equal 1, then these terms are all 1. And then we just see that's just the expectation value of, so it's of the sum of I times pi. So the derivative df over ds at the position s equal 1, that's just our expectation value. And now we can see what do we have with the second derivative. If we take the second derivative, df over ds squared at s equal 1. So we take the second derivative at s equal 1, this cancels. So, but this is the expectation value of x times x minus 1. Or you could also write it as expectation of x squared minus the expectation value of x. So actually take care, this is not the variance, because it looks a little bit like the variance, but in the variance we would take here the second power of the expectation value of x. When we get something similar, so basically we see if we take our function at position 1 and take all the derivatives, we find some typical moments. The slope at 1 is the expectation value, the curvature at position 1 is here this combination of moments, and in general we can say the kth derivative of our generating function at 1 is just the expectation value of x times x minus 1, and so on and so forth until x minus k plus 1. And this you see, if you just take here higher derivatives, you come to this formula. So now maybe as an application, very often we are interested in the variance. So what's with the variance? The variance of our random number x, we know it's the expectation of x squared minus the expectation of x and then squared. Our generating function gives us this here, and then you can see we can you can see it directly, and we can write this as expectation of x times x minus 1, because this is what we get from the generating function. But then what we have here subtracted, we have to add again, so we have to add the expectation value of x. So this is really the expectation value of x squared, and then we still have to subtract minus the expectation value of x squared. And this first here is the second derivative of our generating function at position 1. This is the first derivative at position 1, and then we have to subtract minus the first derivative at 1 squared. And this is the variance of x. This formula is important because we very often are not interested in general moments but in the variance, and then we have this formula here. So basically this would be enough, but maybe I give you just one last thing. Sometimes we want to have the moments directly, so like when we take the higher derivative, we just get a combination of moments. How do we get the moments directly? And this is when we get this if we take not only the derivative but multiply this by s. So if we take this operator s times d over ds, yeah, and we apply this to our generating function, and this gives us here the sum n s to power n pn. Now I sum over n, so it's this same as before, but now I just for variation used, instead of I used n, but we don't have s to I minus 1 because we multiply this s, we have s to n, and then we know we can work this out, and you see that we can write down the kth moment of our generating function we obtain if we take this operator s times d over ds, we apply this operator k times to our generating function and take this as the position s equal 1, and then we obtain our moments. So this video was getting maybe a bit large, but at least now I was giving you all the important formula for our generating functions. We can calculate the moments, the variance, or with this formula we know how to extract all our probabilities at the behavior and the slopes at position 0. And of course now you might wonder why we do this at all, and just bear with me, this is just a very cool technique, because very often it's more easy to construct this function and then later to recover the properties of our distribution. So, and now in the next videos I will show you some very simple examples of discrete probability distributions. Thank you.